Yeah. Okay. Welcome. Hello, everyone. Welcome to another AISC Spotlight event. My name is Alireza Darbehani, and I'll be your host today. Our today's talk is around MAST, a memory augmented self-supervised tracker. Before I introduce our speaker and facilitator, I would like to announce that the ACE has a great upcoming 6-week workshop called Practical Natural Language Processing, which within 6 weeks you will learn a lot of stuff around machine learning and natural language processing, as well as building a capstone project. So our speaker today is Soufia Naseri. She's a machine learning engineer with a master's degree in machine learning. She's currently working with an AI company focused data. Our facilitator today, Fatemeh, is a graduate student in computer science at University of Toronto and Vector Institute. She's passionate about applications of machine learning in healthcare and applying computer vision methods on medical images for predictions. Without further ado, Soufia, please get us started.
Thank you, Ali. Hi, everyone. I'm Soufia. I'll be presenting MAST, a memory augmented self-supervised tracker. I hope you enjoy it. So I'm just going to give you an introduction of what tracking is and a couple of the applications with a bit of understanding of those learning approaches. Some of the prior approaches that it's been done before this paper, and also a proposed solution of this paper and how they implemented it. Then going over our results and their major findings. Okay, so here's the application of tracking. It's essentially tracks the moving objects and they follow it dynamically across the video frames. On the right side, you see human detection and how it's tracking it. This is good for shoplifting, and I've seen during this time COVID, part of it becomes that they make sure there's a 6 feet apart distance of them. They're using tracking as well. There's another human-computer interaction which I find fascinating. It's the way that you communicate and your computer and however it tracks your movement of those hand gestures. So for video tracking, there would be different categories for it. In general, video tracking would be into two main categories. One of them would be supervised learning, and the other one would be semi-supervised training. In a supervised training, as you know, imagine that you have your inputs as your images and your masks as your output or annotated, essentially. Have in mind that this could be like a unit architect that you input your image and your output would be essentially a mask itself. For this supervised, you have to provide annotated frames to it, and just there are a lot of annotation involved. For semi-supervised training, however, you have your images and there's different frames of, let's say, video, and you would annotate few of those images, and you would learn algorithmically how to find the next masks or the next segmentation, pixel level segmentation. There are issues with all of these categories, so like there are trade-offs to it. The supervised model, it's very memory intensive, and as you see here, there's about on average more than 1 million hand annotation on a pixel level, and they're reaching somewhat good accuracy, some of them much lower, and some of these approaches here are semi-supervised and self-supervised models. They're also computationally intense, and because it goes frame by frame, it has to predict frame by frame prediction. It uses a lot of hardware, and it causes a lot of bottlenecks in the hardware. So that's just so you would know, there are always trade-offs to all these features. But I would say, personally, I would be okay with choosing this one because hardware's getting better, technology is improving. smaller memories with much faster clock rates. In supervised, you got to do hand annotation at all time. For better representation of what this paper would do, I've written this in a form that you would have, let's say, a tracking task. One of them, as most people are familiar with, is visual object tracking, which essentially the bounding box. And the next one would be the supervised visual object segmentation, which we call semi-bus, or AKA dense tracking. For that dense tracking, there are two methods that is usually used traditionally. They're point-based, segmentation-based, and there's another based on propagation. So segmentation one is the one I showed you. It uses based on well, I go into it more in a few slides, but segmentation based is essentially on a pixel level, and propagation based, it uses somewhat of memory to come up with the next masks. So this paper, what they call it self-supervised, it essentially uses both propagation based and segmentation based. Okay. So for that segmentation based, what you do essentially, you have your models and you have your images, right? And you have your masks here as the pixel level annotated. A segmentation model is essentially your encoder of that model. When you have a model, you have your input as image, and you have your masks as your output. And segmentation model would be the encoder. For this, there's a trade-off again, because when you're using segmentation model, when you're using different classes, you have to do fine-tuning of that training again. You have to remove the last layer, retrain it, change any output layers and whatnot to be able to make it work for your application. Okay, then, sorry, go ahead. Okay, okay. I can hold it like this. Is it better? Okay, okay. No problem. Thanks for letting me know. Okay. So that was the segmentation. I thought you had a question about that. So for propagation based, it's what it does. It's based on it uses dynamically on a frame to frame basis approach, and how it does is, let's say we have an image, and you have a mask for it. To predict whatever the next mask should be, it uses some sort of algorithm and learning here to recognize what to predict and what to essentially segment or for your pixels, what pixels should be tracked. And this way would be kind of dynamically flowed from frame to frame to be able to do this task. So part of the work of that memory augmented model has been mostly done using sequence models, which you might be familiar with GRUs or the LSTMs. They're essentially uses that kind of, in the image that you're using those pixels and memories and what it's changing and whatnot to do some feature extraction with those and apply it for their next frames. This paper uses a very good mechanism, which is called attention mechanism. Essentially, attention, we would go more into the attention mechanism, but it's for retrieving candidates of those frames to just know which one to pick and what to make, I would say, what to give more attention to in terms of pixels and the area of interest. Okay, so this is actually pretty cool. I don't know if anyone has done it. I've never done it before, so I became familiar with it throughout this paper. Essentially, what they're using, they make one change and it applies throughout their network. It brings up their accuracy a bit higher. One basic thing is that when working with RGB colors, when you have your space color as RGB, they're highly correlated together. As you see in the picture A, B versus G is blue ones, the green ones, the green versus red. And these are how green pixels and red pixels are correlating together. With this model, learns little complementary information for tracking, especially because there would be a problem with this in tracking, in a sense that if you have a frame, if you have your current frame, and your model learns what colors should follow for the next frame rather than what objects. So it sometimes maps similar colors, uh, similar color pixels together. However, they're different objects. This would cause issues and a lot of mistracking in that sense. It won't be accurate. It won't be tracking what you want to track. So essentially, they changed the color space to lab, and lab stands for that. It's a it's a four color space rather than the RGB. And what it does, it essentially makes a difference of that lightness. So you have your lightness as L, and A, I believe they work with magenta and blue, maybe. Oh, sorry, magenta and green, and blue has two color space of blue and yellow. This way, uh, it's not as highly correlated as you see. It's much less correlated together. This way, if when they're during training, they drop one of those input channel for it to actually map it to the object rather than color to color. And they can do it by removing just one color and not affecting everything else because it's less correlated. Okay, so then about attention mechanism. The attention mechanism essentially is working with a triplet. It's a QKV, stands for query, keys, and your values. Um, the way the approximate, so I is your current frame, I is your picture, and T is your current frame. I is the pixel of that current frame. And this is estimation of the pixel of that current frame, which would be a summation of your affinity scores across your pixels, and affinity scores is similar as similarity matrix, if you want. And it multiplies it with that value, and value stands for your previous your reference frame or your previous frame. When it multiplies it together, it gets an estimation of it. And essentially, your affinity matrix or the similarity matrix is just a softmax of finding those query maxes and your keyframes. Keyframes are your reference frames, and it gets an affinity scores based on that, and it multiplies it with your raw reference frame or the previous frame, which would be estimated. I can, okay. And for one important thing that you're using also, again, adds up to their accuracy. It's they're using Uber loss, and Uber loss is very good for regression based. And essentially, this tracking and approximation of those pixel tracking is a regression problem because you're approximately you're doing an estimation of those values rather than a classification point of view. So the way it does, that's your reconstructed or the estimated image or the pixels with your real of what it should be. So the Uber loss essentially gets that they put a range of it from 1 to negative, sorry, it's from 0 to 2, I believe. So the maximum loss over here, if you were to choose, if this was 1 and this was -1, here would be, if here would be 0, sorry, okay, if this was 1 and this was -1, essentially you would do a maximum of 0.5 here, but in traditional mean square error, when you're doing a square error here, you would essentially get 4. So 0.5 versus 5 is a difference in a sense that they want to pay less attention to outliers. And this is a value that they choose. And Hoover loss is important, what value you choose for your outliers. So essentially, they're saying that they don't want to pay attention, they want to pay less attention to the outliers, and that's what makes their loss very good in a sense that they would look for change in those little change in those similarities. Um, and I can make a pause here if you have any questions, or Ali, would you like to collect questions on that?
Yeah, we have a couple of questions here from our audience. The first one, I'm not sure if you can briefly explain it. Someone asked, how can self-supervised be used in a single object tracking?
One single object tracking. I have actually an example here. Next page is it. So this wall is actually being tracked just using that self-supervised. So here, I gotta do more explanation on this, but essentially your frame, you're using memory of what it's been moving throughout your frame, and what's the interest, what's that region of interest of that frame being changed and whatnot, and it would select those pixels. That's essentially it. If you want to look for a selected let's say object, you can make you can essentially train it based on some sort of selections. I saw a video of it that there is like 4 to 5 sheeps in a circle, and there's a dog running around. So I don't know how they're choosing that selective sheep, but it is doable in a sense that they're selecting just 3 of those sheeps, and not the dog or the other sheep. And once they go out of these circles that they should be, they are being tracked of wherever they're going. Um, it's it's important to mention that these sheeps were selected before, like they show that they wanna, they're looking for this kind of sheep to track. So I believe that would come to a pre-processing before that training model starts. Does that make sense? I hope that I
Yeah.
hope that makes sense. Yeah.
Okay, the next question is the color space transformation part of the model, or it should be done beforehand?
Color. So what they're doing, they're dropping a color. They're dropping color randomly. So they're doing it while training. That's my understanding, because they're here again. They want to make their model robust. They don't want it to learn colors. So they're dropping it randomly, but one of these channels, right? So either A or B, one of them would be dropped. So the model won't learn won't learn how to map the colors and just learn what are the objects.
Great. So the last question for this part, is the attention mechanism applied to the entire image or just the region of interest?
So very good questions. We'll get to it more, but just to give you a quick answer, it's applied to a region of interest.
Awesome.
Mm-hmm.
You can continue.
Okay. Okay. So here's their main training and some of those inference results. Again, we're using query key values to do training. Essentially, so how the algorithm works, let me give a walkthrough of how the algorithm works. Essentially, you give your target frame to an encoder, and this encoder is coming from Siamese network. So once you give this network, this frame to your encoder, you give a bunch of queries for, which we call reference frames of, let's say, Q1 to QM. And then using these K, and K again, K and K are your keys, and how the model is treating it as memory. So essentially these Ks is coming from a memory in your model. So this K and K, because they've been using encoder, they are representing feature representation, and they're using a shared weight feature extractor. So once you have your Q1 to QM, you're looking at Ks, and here Ks, you would use attention mechanism to figure out your region of interest, and then it retrieves your pixel values. So how it does it? It computes a similarity matrix between your Qs and Ks, or your region of interest, as we call it. So it would be your target frame versus your region of interest, and then it outputs the weighted region, or whatever the region is more, whatever the affinity scores is more weighted on that region of interest. So value, when you're doing training, as you can see here, is just that image frame itself. But during inference and when you're doing testing, it would be just the mask. It would be the mask and just that segmented in pixels, which has came from that region of interest. Okay, this we can maybe pass on. Oh, one information that I want to give in. So again, encoder that they're using Resonate 18, just the architecture itself. And once they train it, they just use that encoder. Okay. So about that region of interest localization, however they do it, they use a query. Let's say this is your query frame, and they pick that query pixel. They run it through. They compare it with their reference frames, and that softmax is essentially your affinity matrix that it's doing. This would create a response map, or what I call a heat map. That it would essentially heat up where the information is important or changing, or less changing because of however their loss has been created. They use a heat map here, and your heat map, again, it's a softmax of that query image. Comparison with the K is your, again, keys or region of interest, where N, you can determine to use a short-term or a longer-term memory. The way they can play around with this is good, because sometimes we want to learn from longer than shorter memories. So this is adjustable. For center, so once they have their heat map, they would run it through a window, or a center would be approximated here. It would again give you let's say rectangular form where your center is here, sitting here, and it approximates based on that region of interest and their affinity scores what the region of interest is. Using bilinear sampler, it extract that region of interest. Okay, for training. For the implementation of training, and I mentioned this, the encoder is implemented using randomly initialized. So they're just using the ResNet 18 architecture, but they're randomly initialize their weights. In terms of training, there are two steps. One of them is the pre-training, and the other step is fine-tuning. For pre-training, it's a batch of 24 of 2 frames fed into the Siamese network, and that 2 frames, one of them is your reference frame, and the other one's your target frame. It's been trained using ADAM optimization for 1 million iterations, also using decay-based learning rates. For fine-tuning, One important thing to mention, they do claim they don't do any fine tuning in a sense that it's not as much intensive fine tuning as others are doing. Whatever fine tuning here means is just that they're using that memory augmented model um, with using multiple reference frame and that target frame inputted to that network. And they fine tune it with a lower uh, learning rate just to fine tune it for their purpose. So it's not much fine tuning they claim as others are doing. For inference, essentially, once your model has been trained and you have your encoder or future representation of the weights, you compute your affinity matrix between the target frame and your reference frame. So that target frame is the testing frame, and that reference frame is whatever you have from memory. Then again, the affinity matrix is used dynamically to create that mask frame by frame. For generalizability, so here, they're doing a very good job with the accuracy in terms of how it's been done. One important thing to mention here, they're on-scene categories. So you have one scene category and one on-scene category. They're outperforming their scene categories. It's very good results, but their on-scene is actually outperforming the other approaches. So their scene outperforms their unscenes, but their unscenes outperforms the other approaches. And they do a calculation of it, of how well they're doing, in a sense that they're penalizing they're actually rewarding if their unseen category is doing uh, much better. Like if it's a high accuracy comparing to their scene, they would reward it. This way, that's just that generalization gap has been measured. There's another adjustment that they've done. Then again, it added to their accuracy, I believe around 2% they mentioned. Is that the traditional approach is that they use bilinear transformation from that sampling of that region of interests. But instead of if your region of interest is here and your sampling center should be here, the sampling center of that CNN kernel would be approximated over here. Sorry, would be approximated over here. But what they added, they used their own sampling method. They don't go much into detail here, but they use their own customization sampling that it would essentially do that, overcome that offsets, and it would add those CNN kernels where the sampling center should be. That's why it added around 2%. Okay, so here's the result of what they've done with their YouTube video list. So all three up here are self-supervised approaches. They continue on here as the supervised method. And the supervised method, among here, they're winning by second, which is very good. As you see, they're doing much better than the supervised method, which contains a lot of annotations. However, they're doing a bit lower than the supervised method, which uses a lot of annotated annotations. So one important thing here is, again, if you look at their generalization gap, they've measured what the generalization gap is throughout other methods. And generalization gap is how well it's doing on unseen ones. It's doing pretty good on unseen ones, second place. And the generalization gap of how their model is robust is 0.4. And the lower number this is, the better this is. And on average, on the supervised method, the number is about 11. Yeah. So conclusion. So the MAST algorithm is actually very accurate. comparing what to providing with the pixel level, and the generalized even better than other methods. The algorithm uses zero semantic annotation, and it's doing much better than other self-supervised methods. And even on scene categories, that performs one of those existing methods for while doing heavy supervision. They're not doing it at all. It's just, again, zero annotation and doing it much better. As computation power grows, high quality of videos are being available, and it's very hard for it to process. But with self-supervised, you can actually accomplish lower task in the sense that you're not using any annotations, and you can just do a lot of more tracking, a lot of more dense tracking, video tracking applications while being generalized and flexible. So essentially, they're being very strong competitor versus their supervised counterparts. Okay, that would be my end of presentation.
Okay, great. Yeah, thanks, Soufia. So we actually have a few questions came in from our audience and the discussion facilitator as well. And I'm not sure if I understand the questions correctly, but just read over. I think the question is, and you kind of answered the question, do you expect to have a good accuracy and robustness when using self-supervised in object tracking compared to pre-trained networks, which I guess the other methods are mentioned here?
So yeah, just to again go over this, their on-scene category is winning the second place. Second place, first being that supervised method, but it uses millions of annotation parts. So there's really very, if you work with this kind of application, you got to do a lot of annotation, and everyone hates annotation. So yeah, I'd say this would work much better. And even on that generalization gap, they're doing much better comparing to even the first one, even the very first annotated supervised method.
Okay, great. So can the model ever perform better on unseen videos compared to seen videos?
Okay, so it depends. Apparently, sometimes it does better, but actually, seen ones, seen categories outperforms unseen. Yeah, usually seen categories is actually outperforms, and this model, same for this model, seen categories is doing better than unseen ones, but not much with kind of diversion, because they do an overall. When you're writing an application, you're doing on an overall purposes, and at the end, you want to do it in inference level that either you've seen less of this object or you haven't seen it at all. And if you can say, okay, I want that object to be tracked, and it just goes track it, then it does a good job.
Thanks. Okay. The next question is about hyperparameter search. How a hyperparameter search have been performed in the model training?
So hyperparameter search for their learning rates. At this time, it's all try and error, of course. So they're not using a specific method that I know of. I just know they use. You gotta fine tune your learning rate, and they just use it to decay this, which is usually good, better than your static one. Yeah, it's all again try and error, but have in mind that this step of try and error, it's almost you have to do it almost for every algorithmic machine learning algorithm that you're doing. You can't just skip the place as of now.
Okay, thank you very much. The last question is around, and I can partially answer that question around the resources like the basically the code repository and a way to replicate the research. So we will post all the links, but I'm not quite sure if there is an open source projects implemented this model.
Last time I checked, there wasn't a code as of now. I suspect that they're either working on it or that they do want something. If they want to make company out of it, I don't know, but they're on hold for. Yeah, they might be able to do that and then probably open source it. As of now, last time I checked, it wasn't available.
Yeah, our facilitator just mentioned there is a GitHub page. So we will post the presentation slides and a link to the GitHub page on the ACE website. If you go to the events page, this current events page on ACE website, you should find all the resources there.
Okay, that's good actually.
Perfect. So if there is no other questions, I would like to thank you, our speaker, Soufia, and our facilitator Fatemeh, for their great job. And thank you for attending the talk. Have a great day, and see you in the next event.
Thank you. Thank you for having me. Bye.
All right, thanks.